Hello dear students, today we are going to learn about combination of capacitors. The heading is given combination of capacitors, but how many types of combinations are there? First of all, we can see here this grouping. When positive end of one capacitor is connected to negative end of the other capacitor, positive end of one capacitor with negative end of the other capacitor, then this grouping, end-to-end grouping, we call it as series combination of capacitors. And if all the positive ends are connected at one point, that is at A, and the negative ends are connected at point B, then only you have two terminals where all the capacitors are being connected. This type of connection we call it as parallel connection. In this topic, we will learn how we can replace. Suppose in an electrical circuit, you have got more than one capacitors and you don't want to use so many capacitors, you want to replace them with a single one. Then that single capacitor which can do the same work or which can function in the same way as together they work, then this capacitor will be called as an equivalent capacitor. Equivalent capacitor. The single capacitor can function exactly the same way as these three of them or more than three, they can work. That's why we need to study this combination of capacitors. Here also, in parallel also, instead of connecting all these three, if we can replace the single one, then that single capacitor will be called as an equivalent capacitor. Equivalent to whom? Equivalent to all the three here. It may be more than 3, 4, 5, 6, 7. Sometimes the connection, there are two types of combination. One is series and one is parallel. But even though there are two types of combination, sometimes you may get it, some are in parallel with each other, some are in series. Like this also you may get it in a circuit. So it may be a combination of series as well as parallel together, but whatever may be the case, this grouping, if we can convert it into a single one, or if we can use a single capacitor which functions the same way as these three capacitors together works, then this single capacitor will be called as an equivalent capacitor. To learn this, how we can replace it with a single capacitor, for us it's necessary to know combination of capacitors. The single capacitor will be called as the equivalent capacitor. Capacitor which is equivalent to the rest capacitors which were arranged together. There are two types of combination. One is your series combination. In series combination of capacitors, suppose this is one capacitor, this is another capacitor, let me take three capacitors. These three capacitors, end to end, if they are connected, negative terminal is connected to positive terminal of this positive plate of this second capacitor, then the second capacitor's negative plate is connected to the positive plate of the third capacitor, and so on. This type of arrangement we call it as series combination. Suppose the potential difference applied at the ends of the capacitor here is V. This is your positive plate plus Q, this is minus Q, this is plus Q, positive plate minus Q, negative plate plus Q, and this is minus Q. And this is C1, first capacitor, C2, second capacitor, C3, the third capacitor. Now as you can see here that the potential at all the three capacitors will not be the same, because these two endpoints of one capacitor is not same with the other two endpoints of the next capacitor, and so on. The potentials are different. So what we do is we the total potential that is applied will be the sum total of V1 plus V2 plus V3. Now if the capacitance of the combined capacitor is written as Cs, is the equivalent capacitance of the combination, then V is equal to Q divided by Cs, that is the total potential will be equal to the total charge on each capacitor divided by the equivalent capacitance, that is Cs. V1 will be the charge divided by capacitance of the first capacitor C1. V2 will be Q divided by the capacitance of the second capacitor, that is C2. V3 will be Q divided by C3 and so on. Now if you put the values of V, V1, V2, V3 here, then you will get it Q divided by Cs is equal to Q divided by C1 plus Q divided by C2 plus Q divided by C3. The Q, if you take it apart, 1 by Cs is equal to Q, take common here, 1 by C1 plus 1 by C2 plus 1 by C3. This Q, if you cancel it, then you get the reciprocal of the combined capacitance in series. 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 and so on. If you have more than 3 capacitors, then it will just go on, plus 1 by C3, 1 by C4, 1 by C5, 1 by C6 and so on. So the resultant capacitance, to find out, we will use this formula, 1 by Cs. The reciprocal of the resultant capacitance is equal to the sum of the reciprocal of the individual capacitances. Then by calculating it, we can find out how to replace this 3 capacitor and use a single one. Now let us talk about or discuss about a parallel combination. In parallel combination, keep the capacitors like this. All the positive ends will connect at one terminal and all the negative ends will connect at the other terminal, so that the potential remains the same. If V is the applied potential, this is your C1, this is C2 and this is C3. This is your positive plate, negative plate, positive plate, negative plate, this is positive plate, negative plate. The total potential, if we take it as V, then all are connected, all the positive ones are connected at one end, the other negative terminals are connected at the other end, so the potential will remain the same. Here what changes is the charge. The charge in each capacitor Q will be the total charge in the whole system. Q will be the sum of the individual charges Q1, Q2 and Q3. If Cp is the equivalent capacitance of the combination, then Q will be equal to V into Cp. Q1 will be potentially same, V into C1. Q2 will be V into C2. Q3 will be V into C3. If you put all the values of Q, Q1, Q2, Q3 here. Then you get VCP is equal to VC1 plus VC2 plus VC3. Then VCP is equal to V, you can take common, C1 plus C2 plus C3. VV, if you cancel it out, CP is equal to C1 plus C2 plus C3. If more than 3 capacitors, then C4, C5, C6 and so on it will go. So the equivalent capacitance in parallel, the CP is equal to the sum of the individual capacitances, C1 plus C2 plus C3 and so on. Now let us discuss about the energy stored in a capacitor. The energy stored in a capacitor is the total amount of work done in charging the capacitor to a given potential. Suppose the small amount of work that is done, let it be dW, in charging in bringing the charge from one plate to the other plate, dW, if I write the small work done, and the charge is suppose dq that you are bringing, and during that time the potential is say V dash. So work done is equal to potential into charge, the charge that you are bringing, and V dash is the potential during the time that you are bringing the charge. And this can be written as V dash is equal to Q dash divided by C. Suppose the charge it was Q dash, and then the charge that you brought is dq. This is the small work done in bringing the small charge dq from one plate to the other plate. Now the total work done in charging the potential, therefore the total work done charging the capacitor from, say initially charge was not there, imagine 0 to total charge in the capacitor is suppose Q. Then we integrate dW, then we will get the work done as W. This is integration of Q dash by C dq. This one you can write as 1 by C integration of Q dash dq. This is 1 by C integration of Q dash dq. That will be Q squared divided by 2. Within the limits that we are taking here is from initial charge 0 to full charge, it is Q. 0 to Q, 0 to Q, the limits are from 0 to Q. Then work done is equal to 1 by C, put the upper limit, that is Q squared divided by 2 minus 0, if you put, it will be 0 squared divided by 2, it will be 0. So you can write this as 1 by 2 Q squared by C. This work done in bringing the charge from one plate to the other plate gives us the measurement of energy that is stored in a capacitor. So this work done gives us the measurement of energy. So you can write energy U, or you can write this W is equal to half of Q squared divided by C. This can also be represented as half of Q into V, total potential, since here V is equal to Q by C. The other way of representing potential energy is U is equal to half of Q. Q is equal to C into V. So if I put in place of Q C into V divided by C, this is squared, you will get half of CV squared. So these are two ways to represent. One way, this is two way, and this is the third way of representing the potential energy, or we call it as the energy that a capacitor can store. The total energy stored when the capacitors are connected in series or in parallel. If you write it as U, it will be applicable for both series as well as in parallel. It is a sum total of all the energies that can be stored by the individual capacitors. Now let us do some numericals based on capacitor. Let us solve this question and see. Find the equivalent capacitance between A and B. These are the plates A and B. Given area of each plate is A. This plate area is A. This area is A. And separation between the plate is D. Separation between these two plates is, say, the whole length is D. The distance between the two plates is D. So what you have to do is, you have to find out the capacitance in region 1, in region 2, and in region 3. And accordingly, if they are in series, then we will use the series combination formula 1 by Cs equal to 1 by C1 plus 1 by C2 to find out the equivalent capacitance. And if they are in parallel, then we will use combined capacitance, resultant capacitance in parallel as C1 plus C2. So before that, first of all, we have to find out the capacitance in this region 1. Solution, when you do capacitance C1, we'll first find out your formula for capacitance C. When a dielectric is placed, it is given by Ka epsilon naught divided by D. So keeping in mind that one, here the dielectric constant is K1, so I'll write K1. The area of the plate is reduced to half. From here to here it is A by 2. I'll write A by 2. Epsilon naught divided by distance of separation from A to B, it is D. So I'll write it as D. So ultimately what you will get here is K1 A epsilon naught divided by 2D. Like that, we'll go to the next dielectric with dielectric constant 3. Now here K1, you know the value of K1. So let us write the value 4. This K1 is equal to 4. So if you write the value here, then you will get 2A epsilon naught divided by D. Like that, capacitance C2. C2 is equal to K2. This is K2. Area of the plate is A by 2. A by 2. Epsilon naught divided by distance of separation is from here to here, it is D by 2. So I'll write D by 2. This 2 you can cancel it out. K2. K2 you have 3. So it is 3A epsilon naught divided by D. Like that, you can find out the capacitance of the third plate. Capacitance C3 is equal to, in this region, third region, you can find out the capacitance. Here it will be K3. Area of separation from here to here is, area of the plate is A by 2 and epsilon naught divided by distance of separation, here also it is D by 2. But K3 here, 2 you can cancel it out. K3 here it is 6, so it will be 6A epsilon naught divided by D. After you find out C1, C2 and C3, here you can say that these two capacitance C2 and C3, they are in series. So C2 and C3, as they are in series, since C2 and C3 are in series, the capacitance let us write it as C dash will be equal to C2 C3 divided by C2 plus C3. Then put the values. C2, it is 3a epsilon naught by d, and C3 is 6a epsilon naught divided by d, then divided by C2 plus C3, 3a epsilon naught divided by d plus 6a epsilon naught divided by d. Then to look like this, 3 6 are 18, a square epsilon naught square divided by d square. Then downside you have LCM d. Then you have 3 plus 6, 9, a epsilon naught. This one, if you reverse it, then it will be 18 a square epsilon naught square divided by d square into d divided by 9a epsilon naught. A epsilon naught one time you can cancel it out. 18, 1d also you can cancel it out. So ultimately you will get 2a epsilon naught divided by d. Now this capacitance C dash, this one in region 2 and 3 combined together with C1, they are in parallel. So the net capacitance since C1 and C dash are in parallel, the resultant capacitance is C is equal to C1 plus C dash. C1 is 2a epsilon naught divided by d plus C dash is also 2a epsilon naught divided by d. So d we take common, it will be 4a epsilon naught. Like this you can find out the capacitance of the whole arrangement or the system. Let us do one more question. In the circuit shown in figure, find the equivalent capacitance. The first thing, as we know that all the capacitors are connected in parallel, so I will do like this. Number one, equivalent capacitance. Let us write it as capacitance in parallel, Cp. It will be the sum of all the individual capacities, 1 plus 2 plus 3, all are in microfarad. So this is 6 microfarad. This is the first part of the question. And the charge stored in each capacitor. Now the charge stored in each capacitor will depend upon their own capacities. Total charge drawn from the battery if you write it as Q, the total charge Q will be the potential V multiplied by the capacitance Cp. This is 100 into 6, it will be in microcoulomb, so it is 600 microcoulomb. This will be the total charge. Now that is drawn from the battery. Now that will be distributed to each of the capacitors individually depending upon their capacitance, 1 microfarad, 2 microfarad, 3 microfarad. So let us find out one by one. Charge in the first capacitor. If you represent it as say Q1, the capacitance is 1, but total capacitance of the combination or the system it is 1 plus 2 plus 3, that is 6, multiplied by the total charge that is drawn from the battery, that is 600 microcoulomb. So you will get here as 100 microcoulomb. Then the second one, the second capacitor, let us write it as Q2, charge stored in second capacitor or charge in the second capacitor. Its capacity is 2 microcoulomb, 2 microfarad. So that Q2 is equal to divided by total capacitance, that is 6 into 600, it will give you 200 microcoulomb. And then charge stored in third capacitor, its capacitance is 3 microfarad. So write Q2 is equal to 3 divided by total capacitance, we have 6 into 600. You cancel 100 into 3 will become 300 microcoulomb. So net charge should be 300 plus 200 plus 100, it should be 600 microcoulomb. So this way you can solve the questions. Thank you and have a nice day.